So far, we defined the geometry of the system, discretized with the particles. We gave a bunch of optimization parameters. We set the interaction potential to be a linear spring with a stiffness of 100 in the units I'm using here, kilonewtons per millimeter. And now we move to this next command here, that is Quickmin, and then a series of parameters. To understand what this command here is, we need to discuss a bit more what kind of optimization we are running. And the optimization that we are running, the data on the optimization that we are running are those are described in, so the type of optimization we're running is described into manuscript, especially part 2 in this case, because we are working with imposed displacements in this example. But let me switch to the board and tell you something about this optimization problem we are working with. So in our problem, we are having this beam here. We are imposing a displacement at the top, which we call U here. And what we will be able to do is to measure the force that we are applying to all the particles that compose this top section of the beam here, as we are progressively increasing U. So if you are plotting the sum of all the vertical forces on all the particles to which you are imposing the displacement as a function of the displacement itself, you end up with a force displacement curve. So you will end up, if you plot the total imposed displacement U as a function of, and as a function of that, the total force of the top particles, so the top particles that you are moving, the total vertical force, well, as you are running a simulation, what you will do is you will start with the undeformed structure and the 3 supports, then you progressively increase a little bit the displacement at the top, and as a result of this incremental displacement, the 3 supports will stay supported, of course, the rest will deflect. This should be straight, while going up a bit. So the 3 supports are blocked, but because you are pushing the top down by a quantity U, you're going to need a force F on these particles, and the beam will progressively deflect until, the simulation will keep increasing the imposed displacement U until obtaining the target imposed U of 0.4 millimeters. So if this is 0.4 millimeters, as you progressively increase the displacement that you are imposing, you will have that the structure will progressively increase the force that is needed until you reach the target displacement of 0.4 millimeters, and then the system will stop. So this is the curve that you are going to obtain, for example, in the first step where K equals 0.3, Ki 0.3 for all particles. Then, what the system will do is compute the energy, so the integral under this curve, that it takes you to go and accumulate this imposed displacement. And then, the target of the optimization is to redistribute Xi among the particles, so that in the next iteration with the new distribution of Xi in the structure, you will actually start with a higher slope. So you are increasing the stiffness of your system. If you do that, when you reach the same displacement imposed, then you will have a higher area. So you are effectively maximizing the area under the force displacement curve when you work with an imposed displacement. And here this is with a different distribution of Xi. And now the optimization code will again restart from the initial configuration, now with a different distribution of Xi, and run again an incremental analysis where a larger and larger U is imposed until reaching the imposed U of 0.4 millimeter, that is our target, and once again the system will have a higher curve here. And you keep, and as the optimization goes, Xi is redistributed until you essentially converge to a maximum force displacement curve that has maximized the structural stiffness, meaning that it has maximized the area under the force displacement curve. Now, the same thing or similar thing happens when you work with an imposed force, which is not the case of this example, but if you were to work with an imposed force, then you could impose the force that you are applying, F imp, and then you can impose the display, and then you can find the displacement. But what the code does in that case is to set immediately the target force and then let the system progressively move at that constant force until finding the equilibrium displacement u. So the first curve will look something like this when xi I equals 0.34 all, and this is the area under the curve. But then if you increase the stiffness of the structure, the second time you will start still with the same imposed force, but you will end up with less displacement. So in that case, when you work with imposed forces and not with imposed displacement, here we are imposing the displacement at the top, but if instead you were imposing the force and measuring the displacement at the top, if you were to do that, then the optimization problem to be solved would be one of minimization of the area. So the optimization is trying to find the minimum of this energy here, whereas in this case here of imposed displacement, you are trying to find the maximum of u. And this is embedded into the software, so you don't have to worry about that. If you are imposing displacement, you are going to run a problem of this kind. If you are imposing forces, you are going to run a problem of that other kind. Another note, what I've shown you here are linear force displacement curves. Well, you get a linear force displacement curve only if you are working with the linear type of interaction. If you're using other types of interactions, like these ones, the E minus X, the weak C, weak T, weak C, or weak, then you would get curves that in general are nonlinear. So if you're imposing a given U imp, while you are running a simulation with the given distribution of x's, you're probably going to get something that is nonlinear. You can look at examples of these in the manuscript part 2, where we are using nonlinear interactions. So let's once again peep into the future and consider what the code is doing every time that we run an optimization. We said that during an optimization, since we are working with imposed displacement, so this case here, the system will start from zero displacement and zero force consequently, and then it will progressively increase the displacement, measuring the corresponding force until reaching the imposed displacement. So for every set of values of xi, we expect that the system will perform a full simulation, the code will perform a full simulation with a progressively increasing displacement and correspondingly increasing force. So this is exactly this graphics that I'm showing you is the initial system with xi equals 0.3 everywhere, as you can read from down here when I hover my mouse on the particles. The three supports are 1, 2, and 3 here, although they are not visualized. The top particles will be pushed down, and what you will see as I scroll the snapshots forward is that the top here will move down slightly. This is the progressively greater imposed displacement that we're applying to the system. And you see that every time I scroll my mouse, the top is indeed coming down. You see? It's deflecting. We are imposing the displacement to the central fifth of this beam. And as a consequence, all the particles in the system are slightly moving. Let me rewind and go back to here. You see that all the particles, if I go back and forth, all the particles in the system are moving, adapting to the imposed displacement through the particle-particle interactions, linear springs, that are everywhere in the system. And then when we reach the imposed displacement, which is here, what is happening is that now we reached the point where we hit the target imposed displacement here, and as a consequence, we ended one simulation, we found the energy under the curve, and we are ready to redistribute the x's of the various particles via the sensitivity method explained in the paper to then start a new curve. So what is happening at this step is that you see the Xi has been redistributed now, the beam is back to the initial position, back to point zero deflection here, ready to reconstruct one step of imposed displacement after the other, the second curve with a greater Xi. And this is what we are seeing happening here. Again, it's deflecting, look at the top here, it's again deflecting down until reaching the minimum, and then again this will create, we're at step 21, this will create a new configuration, and so forth, every time moving the Xi through towards a 0-1 solution, and every time repeating this deflection, this imposed deflection, to measure the forces and so the energy, the strain energy in the system. So all this long introduction is to come and tell you what this command is doing. So Quickmin is the method by which the code performs this incremental simulation, by which the displacement is progressively increased, and every time the imposed displacement is increased, the particles are rearranging based on their interaction. So the method to find the position of static equilibrium as the displacement progressively increases until reaching the end, this method is called Quickmin. There is a reference to the paper where this method is described. You can find the reference in the manuscript part 1 and possibly in the manuscript part 2 as well. And the rest of the parameters that are needed to run this simulation that is performed at each step of the optimization. So the optimization is the redistribution of X's to maximize the strain energy. The minimization is the method that allows you to equilibrate the system under the imposed displacement for any given distribution of Xi. So 10 to the minus 9 is the description of the parameter is given here. This is the tolerance. So the Quickmin is considered as converged, so the system is in static equilibrium where the particles, when they move and rearranged under the imposed displacement, when they don't change the internal energy more than 1/1000th of the previous value. So it's a strict criterion to say the system has converged to a static position. Average is just a criterion so that you don't just look at the difference between the last strain energy and the strain energy in the previous step of the minimizer, of the Quickmin, but you average it over 10 steps. It's a way to make the process more stable, and it is described in the manuscript part 1. More interesting parameters are these two here. D max is the maximum displacement that you allow any particle to take from one step of the generic minimization to the other. So let's look at the first minimization from step 1 to 10. This is as the particles are moving. This is actually a collection of many displacement of each particle, because each snapshot here, as we will see soon, are actually 10,000 integrations of the displacement of the particles. Well, we are setting a limit where at each step of this integration, the particle at the maximum can move by a small quantity, in this case 0.02 in units of length that for us are millimeters in this example. So this is just to avoid that the particle moves very widely because it may be under a high force, and this could make the simulation crash. So it lets the system move slowly to keep it stable. DT is because this Quickmin method requires a time step, so you have to attribute a time step to it. And the good estimate of time is approximately 0.01 times the square root of the mass of a generic particle divided by the stiffness of the interaction potential. So in our case, 0.01, if you take the square root of the mass was 3 grams, so we attributed it here. The stiffness of the potential is here, so if you do this calculation, you see that more or less this 0.02 is in the right range. It's just an indicative quantity, so you can be more precise by so my suggestion is you take this as an initial guess, you see whether the system is converging properly or not. If it is not, you make the step smaller. If you see that there are some problems, it's behaving erratically, you change this value. 10,000 is every how many steps do you want to produce output. We will see later what are the outputs that are being produced, but one of the output is the one that I was showing to you in this video here. It's a snapshot, a frame in this video. So every time we advance by one frame here, we are actually advancing by 10,000 particle displacements in this process that is looking for equilibrium under the imposed displacement. Okay? So if you want to make your output file lighter, to save less often and make the output file less smaller, then you can put a large number here. If you want to save very frequently and get a very fine video of the deflection, then you can put a smaller number here, maybe save every 1000 steps. But this will produce large output files that may be difficult to manage. Finally, yes or no here, this is telling you whether you want to create files that you can visualize in this way for all the steps during the simulator. Usually it's a good practice to keep this as a no, but there are some situations where you want to put it as yes. For instance, now I want to show you the deflection of a beam in between the different steps of the optimization, so when she is fixed and we are looking for equilibrium. And so just to show you this, I take this to be yes. But in general, when you just look at the results of an optimization, when you are confident that the system is going equilibrated properly, then you don't need to produce this output file that can be very demanding and very large. So you can use a no here. I suggest you use no except when there is a good reason for you to look at the details of how the system is deforming under the imposed load or imposed force.